What if some of humanity's greatest leaps forward in space exploration happened completely in secret, their stories buried in classified files and forgotten launch records? Think about the technologies we take for granted today: the GPS that guides your road trips, the weather forecasts that plan your weekends, the satellite images that reveal our changing planet. Many of these innovations didn't emerge from high-profile moon landings or celebrated Mars rovers, but from shadowy missions that vanished from public view almost as soon as they began. For every Apollo program that captured the world's imagination, there were dozens of covert projects operating in the background, silently reshaping our future without anyone noticing. Space history isn't just a record of brilliant successes and very public failures. It's also filled with hidden chapters: missions launched under false pretenses, satellites that gathered intelligence while pretending to study stars, and probes that disappeared without explanation, only to quietly advance our understanding of the universe. These endeavors operated in the gray zones between science and espionage, between exploration and military strategy, their true purposes known only to a handful of people behind locked doors. Yet their impacts echo through our daily lives, influencing everything from international security to the smartphone in your pocket. In this video, we're pulling back the curtain on 21 of these lost space missions, from Cold War relics that monitored nuclear threats to modern satellites that still operate under layers of classification. We'll explore how a failed lunar probe secretly perfected landing techniques that would later enable Mars rovers, how a scientific satellite doubled as a nuclear watchdog, and how forgotten Soviet experiments paved the way for tomorrow's interstellar travel. This isn't just a story about rockets and satellites. It's about how ambition, secrecy, and curiosity intertwined to create breakthroughs that changed our world while remaining invisible to the public eye. So join us as we journey back to the tense era of the Cold War, where hidden ambitions first reached for the stars and set the stage for decades of covert discovery. But to truly grasp how these missions stayed hidden, we need to step back into the heart of the 20th century, a time when the world was divided by ideology and the heavens became the newest battlefield. The Cold War space race is often remembered for its iconic public spectacles: Sputnik's first beep, Gagarin's historic orbit, Armstrong's giant leap for mankind. Yet behind these celebrated achievements raged a silent, parallel conflict fought not for flags and glory, but for information and advantage. This was a shadow war where technological one-upmanship was the primary objective, and secrecy was the most powerful weapon. Both the United States and the Soviet Union operated with dual-purpose agendas, masterfully balancing public-facing scientific exploration with deeply classified military and intelligence operations. A satellite publicly touted for studying solar flares might secretly be tuning its instruments to eavesdrop on military radar frequencies. A rocket launch billed as a test for a new communications system could actually be carrying a sophisticated camera designed to peer down on rival missile silos. This required an unprecedented level of collaboration between civilian space agencies and national defense departments, creating a blurred line between astronaut and spy, between observatory and listening post. This environment fostered a unique culture of deception and misdirection. Launches were scheduled from remote, secure facilities under vague pretenses. Communication streams were heavily encrypted, with data flowing only to a select few with the highest security clearances. Missions that failed were often quietly written off as losses, their true objectives buried in classified archives. Meanwhile, missions that succeeded simply vanished into the operational background, their contributions known only to a small circle of planners and analysts. This foundational context of suspicion and competition is the essential key that unlocks the stories of these lost missions. It explains why their breakthroughs were kept secret, why their failures were obscured, and why their profound impact on our modern world has remained, until now, almost entirely unnoticed. In the tense summer of 1960, as the world nervously watched the skies for signs of conflict, the United States launched a small, unassuming satellite that would quietly make history. Officially, it was known as SOLRAD-1, part of a new program to study solar radiation and its effects on radio communications. But hidden within its scientific shell was a revolutionary secret: the very first electronic intelligence satellite, codenamed GRB for Galactic Radiation and Background. Its public mission was a perfect cover story, believable and beneficial to science, but its real purpose was to drift silently over the Soviet Union and listen. While its solar sensors pointed sunward, its clandestine payload was tuned to Earth, scanning for the electronic fingerprints of Soviet air defense radars. Each time it passed over enemy territory, it collected the frequencies, pulse rates, and locations of these critical systems, storing the data on tape recorders until it could transmit the intelligence back to waiting analysts in the United States. The brilliance of GRB was in its duality. By piggybacking on a legitimate scientific mission, it solved one of the biggest challenges of early espionage: plausible deniability. The Soviets could track the satellite, but they would assume it was merely studying the sun. This deception provided a layer of protection and allowed the program to continue gathering vital information for over a year. The intelligence it returned was nothing short of transformative. For the first time, American strategists could map the vast and secretive Soviet air defense network from the safety of space. They learned its coverage gaps, its technical capabilities, and its operational patterns, knowledge that was absolutely priceless for planning potential bomber routes and later for assessing missile threats. This was a strategic advantage born not from a louder rocket or a bigger warhead, but from superior information gathered in utter secrecy hundreds of miles above the Earth. Despite its profound impact, the truth about GRB remained locked away in classified vaults for decades. The engineers and scientists who worked on it were bound by secrecy oaths, and the satellite itself was simply forgotten by the public, its story eclipsed by the more dramatic manned spaceflights that followed. Yet, its legacy is woven into the fabric of our modern world. GRB proved the fundamental concept of signals intelligence from space, establishing a template that would be refined and expanded upon for generations. It was the direct ancestor of the vast, sophisticated satellite constellations that now monitor global communications, enforce treaties, and provide early warning of threats. This unassuming pioneer demonstrated that the ultimate high ground wasn't just for looking down, but for listening in, forever blurring the line between scientific discovery and national security, and setting a precedent for the covert operations that would follow. While GRB was listening to Soviet radar, another American program was preparing to open its eyes for the very first time. This mission, codenamed Corona, would become the ghostly gatherer of visual intelligence from the heavens, a project so secret that its very existence was denied for over 30 years. Beginning in 1959, the United States launched a series of satellites under the public guise of the Discoverer program, which was charmingly presented as a noble effort to advance space science and biological research. The official story often involved launching small animals or scientific instruments into orbit, a narrative the press and public readily accepted, but the truth was far more strategic. Hidden within these innocuous shells were the most advanced spy cameras of their era, pointed not at the stars, but directly down at the Earth, focused with intense precision on the vast and mysterious territories of the Soviet Union. The technological challenge was immense. This was years before digital imaging. You couldn't simply beam a picture back to Earth. The Corona team had to invent an entirely new process from scratch. Their brilliant, audacious solution was a film return capsule. The satellite would fly over its target, its powerful camera snapping thousands of feet of high-resolution film. Once the film was fully exposed, the satellite would then jettison a heavily shielded capsule containing all that precious imagery. This capsule, nicknamed the Bucket, would plunge back through the Earth's atmosphere, deploying a parachute to slow its descent in midair. Then, in a maneuver straight out of a Hollywood thriller, a specially equipped cargo plane would fly beneath it, trailing a long cable with a hook designed to snag the parachute lines and reel the bucket in, literally catching intelligence as it fell from the sky. The first dozen or so attempts ended in failure: missed catches, crashed capsules, malfunctioning cameras. But with each setback, the engineers learned, adapted, and improved. Finally, in August 1960, a mission code named Discoverer 14 succeeded. For the first time in history, a plane snagged a capsule full of photographic film that had been developed in orbit. The images it contained were a revelation. They provided the first clear, overhead look at Soviet military installations, airfields, and industrial complexes. This single mission effectively dismantled the politically charged missile gap theory, a widespread fear that the Soviets had built a commanding lead in intercontinental ballistic missiles. The Corona imagery proved conclusively that this gap was a myth. American intelligence had been vastly overestimating Soviet capabilities. This single fact alone calmed Cold War tensions and allowed for more rational military planning and budgeting. But Corona's finest hour came during the terrifying 13 days of the Cuban Missile Crisis in 1962. As the world stood on the brink of nuclear war, Corona satellites provided irrefutable photographic evidence of Soviet missile sites being constructed in Cuba. They also delivered the equally crucial follow-up imagery that confirmed the sites were being dismantled, providing the hard proof needed to de-escalate the crisis. This wasn't just helpful intelligence, it was a critical tool that helped prevent a global catastrophe, all while the public remained completely unaware of the silent sentinel overhead. The legacy of Corona extends far beyond its Cold War espionage role. The incredible photographic technology developed in secret, the razor-sharp lenses, the precise orbital mapping, the techniques for analyzing aerial imagery became the foundation for the entire field of civilian remote sensing. The satellites that now map our planet for Google Earth monitor deforestation in the Amazon, track agricultural harvests, and help us respond to natural disasters all owe a debt to this clandestine pioneer. Corona proved that a picture from space could not only win a geopolitical argument, but could also fundamentally change our understanding of our own world. It set the undeniable precedent that space was the ultimate vantage point, a truth that both superpowers recognized instantly, leading them to develop their own parallel and equally secret eyes in the sky. Even as Corona film canisters were being snatched from the sky over the Pacific, an almost identical drama was unfolding on the other side of the world, hidden behind the Iron Curtain. The Soviet Union, facing the same desperate need to see what its adversary was building, launched its own secret eye in the sky. This was the Zenit program, a masterpiece of Cold War deception that perfectly mirrored America's clandestine efforts. To the outside world, the launches were announced as part of the triumphant Vostok program, the very same series that had carried Yuri Gagarin into history as the first human in space. The public and the press were told that these were further tests of the Vostok spacecraft, sometimes even that they carried biological payloads or dummy cosmonauts. It was a brilliant cover story, leveraging the glory of the manned space program to conceal a military mission of immense importance. In reality, the Zenit satellites were robotic spies, their hulls packed not with a hero cosmonaut, but with an array of powerful cameras, film magazines, and a single-minded purpose: to photograph every NATO airbase, naval port, and missile site in stunning detail. The technological parallels to Corona were striking, yet the Zenit system had its own unique and ingenious engineering. Like its American counterpart, it relied on physical film that had to be returned to Earth. After its mission was complete, the satellite would orient itself and fire retro-rockets, sending a specially designed re-entry capsule screaming back through the atmosphere. But instead of a daring mid-air capture, the Soviets opted for a land recovery on their own vast territory. The capsule would parachute down onto the steppes of Kazakhstan, where recovery teams would race to secure it. This method avoided the complex aerial ballet, but introduced its own challenges, as the capsules sometimes landed in brutally remote or difficult terrain. The cameras inside these satellites were formidable pieces of technology, capable of resolving objects on the ground down to a few meters in size from orbits over 100 miles high. This gave Soviet planners an unprecedented look at Western military preparedness, allowing them to verify intelligence, monitor ship movements, and track construction at key facilities. For years, the existence of these dedicated spy satellites was one of the Soviet space program's most closely guarded secrets, with every launch and recovery conducted under a veil of absolute silence and misdirection. The legacy of Zenit, however, extends far beyond the black and white images it delivered to Kremlin analysts. The relentless cycle of launch, photography, and recovery created an incredible feedback loop of engineering innovation. The re-entry techniques perfected for bringing the film capsules back safely directly informed the design of later manned Soyuz spacecraft, ensuring the safe return of actual cosmonauts. The rigorous demands of space-based photography pushed the development of higher-resolution lenses, more stable pointing systems, and better film. Furthermore, the very need to hide these missions accelerated advances in what we would now call stealth technology for space. The Soviets became adept at masking the true purpose of their satellites, using deceptive orbits and radio silence to avoid tipping their hand to Western observers tracking their every move. This culture of secrecy and technological one-upmanship, happening in parallel with identical efforts in the United States, created a strange form of collaboration. Though neither side knew the full details of the other's capabilities, they were locked in a dance, each advance by one driving a counter-advance by the other. Together, in the shadows, they collectively pushed the entire field of satellite technology forward at a breathtaking pace, proving that even in the depths of the Cold War, progress could be a silent, two-way street. While American eyes were fixed on their own spy satellites, the Soviet space program was aiming for a much more distant and desolate target, the surface of the Moon. In early 1963, a modified Soviet rocket lifted off from the Baikonur Cosmodrome, carrying a probe designated Lunar E6 No. 2. Its publicly stated mission was ambitious and scientific, to achieve the first ever soft landing on another celestial body. The world watched with bated breath, but just minutes after launch, the mission was over. A failure in the rocket's guidance system sent the probe tumbling back to Earth, where it burned up in the atmosphere. To the public and to Western observers, it was just another embarrassing and forgettable setback in the difficult early days of lunar exploration, another lost mission quickly filed away and forgotten. But that public failure was a carefully constructed illusion, a smokescreen hiding a much deeper and more significant truth. behind the scenes, the engineers of the Soviet space program were not dismayed. In fact, they were learning. The Lunar E6 program was never just about a single, dramatic landing. It was a meticulous, step-by-step campaign to solve one of the most complex problems in spaceflight: how to gently lower a fragile machine onto an alien world with no atmosphere to help slow it down. The probe that was lost was packed with experimental technology, including a brand new guidance computer and a sophisticated propulsion system designed to fire retro rockets at just the right moment to cancel out its tremendous speed. The launch itself was a critical test of these systems under real-world conditions. Even in its brief flight, the probe transmitted a flood of valuable engineering data back to its creators. It revealed flaws in the rocket's avionics, provided insights into the stresses of launch on the delicate landing systems, and offered a brutal but invaluable lesson in the unforgiving precision required for space navigation. This so-called failure provided the essential blueprint for what needed to be fixed. 3 years and several more unsuccessful launches later, that accumulated knowledge culminated in one of the most pivotal moments in space history. In January 1966, Lunar 9 finally succeeded. It fired its retro-rockets, inflated its airbag-like landing apparatus, and touched down gently on the lunar soil in the ocean of storms. It then opened its petals like a strange metallic flower and transmitted the very first panoramic photographs from the surface of the moon. The world was mesmerized by the grainy images of a desolate, rocky horizon. What they didn't see was the ghost of Lunar E6 number 2 in every single step of that triumph. The guidance algorithms that calculated the descent, the engine performance data that determined the burn time, the structural reinforcements to the probe's body, all of these were direct results of the hard lessons learned from the missions that had publicly vanished without a trace. The influence of this quiet engineering victory did not stop at the Soviet border. Across the world, American scientists at NASA, a jet propulsion laboratory, were paying very close attention. The United States was deep into planning its own robotic lunar landing program called Surveyor, which was tasked with scouting out safe landing sites for the upcoming Apollo astronauts. The success of Lunar 9 sent a shockwave through the American program. It proved that a soft landing was not only possible but achievable. More importantly, the technical details of the Soviet landing, which were eagerly analyzed by Western intelligence, provided NASA engineers with crucial real-world data. They could see what landing systems worked, and by reverse engineering the problems the Soviets had likely overcome, they could anticipate and avoid similar pitfalls in their own designs. The failure of one mission in 1963 had quietly become a foundational lesson for two rival superpowers, dramatically accelerating the pace of exploration for everyone and proving that in the race to the moon, there were no true failures, only lessons written in fire and metal on the road to success. While the world looked up at the stars with OAO2, believing it was a pure scientific endeavor, its instruments were also looking down, watching for the faint, telltale flashes of humanity's most destructive potential. Launched in 1968, the orbiting Astronomical Observatory 2 was a technological marvel of its time, a sophisticated platform designed to open a new window on the universe by studying ultraviolet light from stars and galaxies, radiation that is completely blocked by Earth's atmosphere. This was a legitimate and thrilling scientific goal, promising to reveal the secrets of hot young stars, energetic nebulae, and the composition of interstellar space. But nestled among its openly celebrated telescopes was a set of sensors with a very different and highly classified purpose: to act as a silent sentinel monitoring for the distinct electromagnetic signatures of nuclear detonations and ballistic missile launches within the Soviet Union. This dual identity made OAO-2 a masterpiece of Cold War engineering. Its primary astronomical sensors, which needed to be exquisitely sensitive to faint cosmic signals, were perfectly suited to also detect the sudden, intense pulse of energy from a nuclear test. The same technology designed to analyze the ultraviolet spectrum of a distant quasar could, with a slight adjustment in its data processing algorithms, identify the unique fingerprint of a missile's exhaust plume against the backdrop of the Earth. Every orbit was a balancing act. For part of its path, it was a pioneering observatory. Its instruments pointed away from our planet, gathering data that would revolutionize our understanding of stellar evolution. Then, as it drifted over areas of strategic interest, it could shift its focus, its hidden payload scanning the terrain below for any sign of treaty violations or hostile activity. The data it gathered was a stream of dual-use intelligence, invaluable to astrophysicists charting the life cycles of stars, and equally critical to military analysts assessing the nuclear readiness of a rival superpower. The success of this hidden mission was profound. By proving that a single satellite platform could so effectively serve two masters, OAO-2 broke down bureaucratic and technological barriers between civilian science and national defense. It demonstrated that the incredibly sensitive and expensive instruments developed for pure research could have immediate and powerful security applications, and vice versa. The techniques for filtering out background noise to find a faint celestial object were directly applicable to isolating the signal of a covert nuclear test from the cacophony of Earth's radio emissions. This convergence accelerated funding and innovation for both fields, creating a feedback loop of technological improvement. The mission's legacy is not just in its astronomical catalogs, but in the very blueprint it created for the modern multi-purpose satellite. Today, countless satellites in orbit perform similar blends of science and security, their full capabilities often known only to a select few, all following the quiet path first forged by this stealthy stargazer. Its story is the ultimate example of a lost mission that hid in plain sight, its greatest contribution to history remaining utterly invisible to the public it secretly helped protect. Just a few months after the triumph of Apollo 11, with the world still buzzing from the spectacle of humans walking on the moon, NASA was poised for another giant leap, this time toward the mysterious red planet Mars. The ambitious plan was a one-two punch of robotic exploration. Two nearly identical spacecraft, Mariner 8 and Mariner 9, were to launch days apart in May of 1971. Their mission was to perform an unprecedented global survey of Mars, mapping its vast cratered deserts, its giant volcanoes, and its enigmatic canyon systems. Mariner 8 was slated to go first, destined to become the dedicated cartographer, its trajectory carefully calculated to sweep over the Martian poles and methodically photograph the entire planet, strip by strip. It was a critical role, and the hopes of the entire scientific community were riding on its success. On the evening of May 8th, the Atlas Centaur rocket carrying Mariner 8 roared to life on its launchpad at Cape Canaveral, its engines painting the Florida sky with fire and promise. But that promise shattered just minutes into the flight. A faulty component in the rocket's guidance system caused a catastrophic failure. Instead of pushing steadily toward space, the vehicle began to tumble, Chinese letter, completely losing stability. The range safety officer, with a heavy heart, had no choice but to send the destruct command, triggering explosives that ripped the failing rocket apart over the Atlantic Ocean. The fragments of Mariner 8, a $100 million machine packed with sophisticated cameras and instruments, plunged into the sea, its mission over before it had even truly begun. To the public and the press, it was a stark, simple, and deeply disappointing failure. Headlines briefly noted the loss, and then the world's attention moved on, filing it away as just another spaceflight setback. But inside the halls of NASA Jet Propulsion Laboratory, there was no time for despair. The launch window for Mars is notoriously unforgiving, opening only for a few weeks every 2 years. The team had a stark deadline: get Mariner 9, the backup spacecraft, ready to launch in just 3 weeks. And it couldn't just launch, its entire mission profile had to be completely rethought on the fly. Mariner 8 was supposed to be the mapper. Mariner 9 was originally designed for a more targeted, closer-look study of specific regions. With its twin now lying at the bottom of the ocean, Mariner 9 had to do both jobs. It had to become the everything mission. Engineers and scientists worked around the clock, furiously rewriting software and reconfiguring the spacecraft's flight plan. They had to calculate a new orbit that would allow its single set of instruments to achieve the global mapping objective while still retaining the flexibility for detailed observation. This was a monumental test of their skill and resilience, a high-pressure engineering scramble born from the ashes of very public failure. When Mariner 9 finally launched successfully on May 30th, it was a different mission than the one originally planned. It was leaner, more focused, and arguably far more robust because of the lessons hard-learned from its predecessor's demise. The investigation into the rocket's failure led to immediate and rigorous changes in quality control for the entire Atlas Centaur program, making the vehicle that launched Mariner 9 significantly more reliable. That increased reliability would become a bedrock principle for all future deep space missions. When the spacecraft arrived at Mars months later, it made history, smoothly sliding into orbit to become the very first human-made object to circle another planet. But its greatest challenge was yet to come. It arrived to find Mars utterly obscured by a global, planet-wide dust storm, a tempest of epic proportions that hid every surface feature from view. The original, simpler mission plan would have been a disaster, its limited timeline expiring before the storm cleared. But the new, flexible orbit and reprogrammed operations plan, a direct result of the post-failure redesign, gave mission controllers a crucial option: they could wait. For over a month, Mariner 9 patiently circled the raging planet, its cameras seeing nothing but a featureless tan ball below. It was a tense and expensive game of orbital waiting, but it paid off spectacularly. When the dust finally settled, Mariner 9's cameras revealed a Mars no one had ever imagined. The largest volcano in the solar system, Olympus Mons, a vast canyon system, Valles Marineris, named in the spacecraft's honor, and ancient riverbeds that suggested a very different, warmer, and wetter past for the red planet. It didn't just map Mars, it completely revolutionized our understanding of it, revealing a dynamic world with a complex geological history. None of this would have been possible with the original, more rigid 2 spacecraft plan. The loss of Mariner 8, a forgotten public failure, had forced a level of ingenuity and redundancy into the Mariner 9 mission that ultimately made it one of the most successful and transformative planetary missions of all time. Its legacy is the very philosophy of robust, flexible exploration that guides every rover and orbiter we send to Mars today. A powerful testament to the idea that our greatest advances are often built upon the quiet foundations of our most frustrating setbacks. While NASA was captivating the world with its sprawling, civilian Skylab station in the early 1970s, a very different kind of outpost was taking shape in secret Soviet workshops. To the public, and even to most of the international space community, the launches of Salyut 2, Salyut 3, and Salyut 5 appeared to be the next logical steps in the USSR's peaceful space station program. They were presented as orbiting laboratories for scientific research, a noble continuation of humanity's journey into the cosmos. but this was a carefully constructed fiction. Behind the shared Salyut name lay a deeply classified black project known as Almaz, which means diamond. This wasn't a laboratory, it was a manned spy station, a formidable orbital fortress designed for one primary purpose: to peer down with a powerful, telescopic eye and gather detailed military intelligence on the United States and its allies. The engineering behind Almaz was staggering, a testament to Cold War ingenuity and paranoia. Each station was built around a single, massive camera system called Agat, a reconnaissance telescope with a mirror over a meter wide. This was not a simple point-and-shoot device. It was a complex instrument capable of capturing incredibly high-resolution photographs of Earth from orbit. Cosmonauts on board would manually aim this giant camera at targets of interest, load large film cassettes, and then process the imagery right there in space. But the most incredible feat was the return method. Since digital transmission was not yet viable for such high-quality images, the exposed film had to be sent back to Earth. The Almaz stations were equipped with small, heavily armored re-entry capsules. Once a film magazine was full, the crew would load it into one of these capsules, jettison it, and watch as it fired its own small rockets, plunged through the atmosphere, and parachuted down onto Soviet territory for recovery. This system combined the discerning eye of a human operator with the hard intelligence product of a film return spy satellite, all packaged into a manned outpost. The men who crewed these secret missions, the covert cosmonauts, operated in a world of half-truths and compartmentalized information. While they were highly trained military officers, they were often not briefed on the full, clandestine scope of their mission. They knew they were operating a powerful camera, but the specific strategic targets and the ultimate use of their photography were need-to-know details held tightly by a small circle of generals in Moscow. Life aboard the Almaz stations was a bizarre mix of mundane space habitation and high-stakes espionage. Cosmonauts conducted their daily exercises and ate their space food, all while carefully maneuvering their station to overfly NATO naval bases and missile silos, capturing imagery that would directly inform Soviet military strategy. To maintain the civilian cover story, they also performed some genuine scientific experiments, but these were always a secondary concern, a sideshow to the main event of observation. The legacy of the Almaz program is woven deeply into the fabric of spaceflight as we know it today. While the stations themselves were eventually retired, the technology and operational concepts they pioneered did not disappear. The core structure of the Almaz station, its durable hull and modular design, became the basis for the core modules of the Mir space station and, later, the Russian segments of the International Space Station. The very idea of a long-duration manned outpost continuously occupied by rotating crews was proven not just for science but for sustained, complex operations in orbit. Almaz demonstrated that humans could live and work effectively in space for months at a time, performing delicate and critical tasks. It blurred the line between explorer and soldier, between a peaceful presence in space and a strategic one, raising questions about the militarization of orbit that are still fiercely debated today. This secret program, hidden behind the friendly name of Salyut, quietly proved that a space station could be far more than a laboratory. It could be a watchtower, a silent sentinel whose true mission was written in film, not in scientific journals. As the era of film-return spy satellites began to wane, a new, even more secretive form of intelligence gathering was taking its place high above the Earth, not with a camera's eye, but with a massive electronic ear. In the early 1970s, as superpower tensions entered a period of cautious détente, the need to understand an adversary's capabilities became more nuanced than simply counting missiles on a launch pad. The United States needed to listen to intercept the very electronic conversations of the Soviet military and political machine. The answer to this problem was not launched from a famous spaceport, but from a secluded pad at Cape Canaveral, hidden under the blandly bureaucratic name of AFP 631, a designation meant to bore any curious observer into looking the other way. This was the birth of the Rhyolite satellite program, a clandestine project so sensitive that its existence was known to only a handful of people within the Central Intelligence Agency and the National Reconnaissance Office. The genius of Rhyolite was in its position and its purpose. Instead of a low, fast-moving orbit that would only allow brief windows of listening time, Rhyolite satellites were placed into a geostationary orbit 22,000 miles above the Earth. At this incredible altitude, a satellite's speed perfectly matches the planet's rotation, making it appear to hang motionless over a single point on the equator. This gave each Rhyolite satellite a permanent, unwavering view of nearly an entire hemisphere. From this lofty perch, its true mission began. Its public cover was that of a scientific satellite studying solar phenomena and monitoring communications for NASA, a story that seemed plausible enough. But its actual payload was a technological marvel of espionage, an enormous parabolic antenna unfurling to a diameter of over 60 feet, making it one of the largest structures ever deployed in space at that time. This giant dish was not for receiving faint signals from distant stars. It was a supremely sensitive ear, finely tuned to the specific radio frequencies used by the Soviet Union for its most secret communications. What Rhyolite listened for was not just military chatter, but something far more valuable: telemetry. Whenever the Soviet Union tested a new intercontinental ballistic missile, the missile itself would broadcast a stream of encrypted data back to its launch controllers, information about its engine performance, its trajectory, its speed, and its guidance systems. By intercepting this raw telemetry data from thousands of miles away, Rhyolite allowed American analysts to reconstruct the entire missile test without ever seeing it. They could learn the missile's true range, its accuracy, its throw weight, and its potential countermeasures. This was intelligence gold, providing a crystal-clear window into the technical capabilities and limitations of the Soviet nuclear arsenal, information that was absolutely critical for arms control negotiations and for calibrating the American strategic response. Beyond missiles, these silent listeners also vacuumed up diplomatic communications and military orders, offering an unprecedented look into the decision-making processes within the Kremlin and Beijing. The program's incredible success, however, was almost its undoing. In 1977, a disgruntled CIA employee named Christopher Boyce, who had worked as a clerk for the contractor building the satellites, began selling the deepest secrets of the Rhyolite program to the Soviet KGB. The betrayal, known as the Year of the Spy, was a catastrophic intelligence breach. It revealed not only the existence and breathtaking capabilities of the satellites, but also their specific orbits and frequencies they monitored. The Soviets were suddenly aware that a significant portion of their most sensitive communications were being intercepted from space. While this forced them to change their codes and encryption methods, the damage was done. The genie was out of the bottle. The public revelation of Rhyolite through the subsequent trial exposed a program that had fundamentally altered the balance of power, providing years of stabilizing intelligence that helped verify treaty compliance and prevent dangerous miscalculations during the most tense periods of the Cold War. Yet the legacy of these silent listeners extends far beyond the world of espionage. The extreme technological challenges of the Rhyolite program, building a receiver sensitive enough to pick up faint signals from 22,000 miles away, developing the massive lightweight antenna structures, and creating the complex signal processing algorithms to filter and decipher the data drove a revolution in satellite communications technology. The same advancements that allowed a spy satellite to pluck a Soviet missile's telemetry from the ether were directly applied to the commercial satellite industry. They enabled the development of more powerful and efficient transponders for television broadcasts, international telephone calls, and global data networks. The very technology that helped keep the peace by listening for signs of war quietly trickled down to become the backbone of our modern connected world, enabling the instant global communication we now take for granted. This clandestine mission, born in the shadows of geopolitical conflict, ultimately helped weave the world closer together. Its most profound impact felt not in secret intelligence briefings, but in living rooms and offices across the planet. After the silent listeners of the Rhyolite program had proven the power of signals intelligence from space, NASA was preparing to turn the world's attention back toward pure science and exploration with what was meant to be a triumphant return to Mars. The Mars Observer mission, launched in September 1992, was not a secret. In fact, it was quite the opposite, a highly publicized flagship-class endeavor that represented the first American journey to the Red Planet in nearly 2 decades. It was a sophisticated school bus-sized spacecraft packed with an impressive array of instruments designed to conduct a comprehensive global survey. Its cameras were to map the entire surface in higher resolution than ever before. Its spectrometers were to analyze the composition of the soil and atmosphere, and its laser altimeter was to chart the topography with breathtaking precision. The scientific community was electrified. This was the mission that would finally answer long-standing questions about Martian geology, climate, and the possibility of ancient water. For 11 months, everything proceeded perfectly. The spacecraft cruised through the void, its systems humming along as it closed the vast distance to its target. Then, just 3 days before it was scheduled to fire its engine and slip into orbit around Mars, all communication abruptly and mysteriously ceased. Mission controllers at the Jet Propulsion Laboratory sent frantic commands, trying every conceivable method to re-establish contact with the silent probe. They hypothesized a catastrophic failure in the propulsion system, perhaps a ruptured fuel line that sent the spacecraft spinning out of control. They considered the possibility of a massive power failure. But without any telemetry data, they were left in the dark, grasping at theories. After months of futile effort, NASA was forced to declare the Mars Observer mission lost. The very public failure was a devastating blow, both financially, with a loss of nearly $1 billion, and emotionally, for the hundreds of scientists and engineers who had invested years of their lives into the project. To the world, it appeared to be a simple, tragic story of ambition meeting the harsh, unforgiving reality of space. But behind the scenes, the story was far from over. The very public nature of the failure triggered a profound and transformative internal reckoning at NASA. The agency's traditional approach of building large, expensive, one-of-a-kind, Battlestar Galactica spacecraft had been called into question. The loss was so total and so costly that it forced a radical rethinking of philosophy. Out of this crisis emerged a powerful new mantra for planetary exploration: faster, better, cheaper. The idea was audacious in its simplicity. Instead of putting all your scientific eggs in one incredibly expensive and complex basket, why not fly multiple, smaller, more focused missions? This approach would accept a higher level of risk on any single mission, but by flying more often, the overall pace of discovery would accelerate, and the loss of one spacecraft would not be a program-ending catastrophe. This philosophical shift, born directly from the ashes of Mars Observer, gave rise to a new generation of missions that would captivate the world. The Mars Pathfinder mission, with its plucky little Sojourner rover, was the first triumphant test of this new model, landing on Mars in 1997 and proving that big science could be done on a small budget. This success paved the way for the Mars exploration rovers, Spirit and Opportunity, which were themselves a pair of missions launched under the faster, better, cheaper umbrella. Their staggering successes, far exceeding their planned 90-day lifetimes, completely rewrote our understanding of Mars as a once wet world and are direct descendants of the lessons learned from the very public failure of their large, silent predecessor. In a very real sense, the spectacular successes of the following decade were only possible because of this one, very loud and very painful failure. Yet, the story of Mars Observer may have an even more clandestine layer. In the years following its disappearance, a persistent rumor has circulated among space observers and historians. The speculation suggests that not all of the technology aboard the spacecraft was purely for civilian science. Mars Observer carried a sophisticated laser altimeter, a powerful imaging system, and robust communications equipment, all technologies with potential dual-use applications for national security. The theory proposes that some of these systems, or the advanced engineering behind them, may have been quietly repurposed or directly influenced the design of classified imaging satellites developed in the same era. While there is no publicly available evidence to confirm this, and NASA has always maintained the mission was purely scientific, the timing and technological overlap make it a compelling footnote. This possibility adds a final, enigmatic twist to the mission's legacy. A very public failure that not only revolutionized how we explore space openly, but may have also quietly contributed to the secret eyes watching over our own world. While the United States was perfecting its silent listeners in geostationary orbit, Soviet engineers were pursuing a far more audacious and dangerous path to technological supremacy, one that promised to revolutionize space travel itself. Deep within the secret design bureaus of the Soviet space program, away from the public celebrations of cosmonaut heroes, teams were working on a new kind of engine, one powered not by chemical combustion, but by the raw, terrifying energy of the atom. This was the nuclear thermal rocket program, a clandestine effort to harness nuclear fission for propulsion, a technology that could theoretically cut the travel time to Mars by half. The most famous of these systems was known as TOPAZ, which stands for Thermionic Experiment in Active Zone. But TOPAZ was just one piece of a much larger and almost entirely hidden puzzle of atomic ambition. The fundamental principle was both simple and brilliant. Instead of burning chemical fuels, a nuclear thermal rocket would use a compact fission reactor to superheat a propellant like liquid hydrogen to extreme temperatures. This superheated gas would then blast out of a nozzle, creating thrust. The efficiency of such a system, measured by what engineers call specific impulse, is vastly superior to the best chemical engines. It's the difference between a speedboat and an ocean liner. One is designed for quick, powerful bursts, while the other is built for efficient, long-duration voyages across vast distances. For the Soviet Union, this wasn't just about scientific prestige. It was viewed as a strategic necessity. A nuclear-powered spacecraft could serve as a rapid response interceptor, capable of quickly maneuvering to inspect or disable enemy satellites. It could also act as a persistent orbital weapons platform, or, in its peaceful application, as the enabling technology for a sustained human presence on Mars. The challenges, however, were monumental and fraught with peril. They weren't just building a reactor, they were building a reactor that could survive the violent shaking of a rocket launch, operate reliably in the vacuum and extreme temperatures of space, and perhaps most dauntingly, be started up and shut down multiple times. The radioactive materials involved posed an immense safety risk. A launch failure could potentially scatter highly enriched uranium across a wide area, creating an environmental and public relations disaster. To mitigate this, the reactors were designed not to become critical and begin the fission process until they were safely in a high, stable orbit, well away from Earth. The Soviet teams conducted numerous ground tests, but the ultimate proof required actually flying these systems in space. Under the cover of the generic Cosmos satellite designation, they did exactly that. Throughout the 1970s and 80s, a series of unassuming satellites were launched from the Baikonur Cosmodrome. To Western trackers, they were just more entries in the long and often mysterious Cosmos catalog, likely military satellites of some kind. But several of these carried active nuclear reactors, including the Topaz systems. These missions were the ultimate high-stakes experiments. In orbit, the reactors were powered up, and teams on the ground monitored their performance, their power output, and their thermal characteristics. They were testing the longevity of the components, the effectiveness of the radiation shielding, and the stability of the entire system in the real environment of space. The data they gathered was priceless, detailing exactly how materials and electronics behaved under the relentless bombardment of neutron radiation and in the intense heat generated by fission. For decades, the full extent of this program and the valuable data it produced remained a closely guarded state secret. This secrecy had a double-edged effect. On one hand, it allowed Soviet engineers to make rapid, focused progress without international scrutiny or political interference. They solved complex problems in reactor design and radiation management that were years ahead of open Western research. On the other hand, this wall of silence prevented the global scientific community from learning from their successes and, just as importantly, from their failures. It stifled potential collaboration and arguably slowed the overall advancement of nuclear propulsion for everyone. It wasn't until after the collapse of the Soviet Union that American scientists were given glimpses into this trove of knowledge, and they were astonished by what had been accomplished in the shadows. The legacy of these secret tests is now quietly fueling the next era of space exploration. When NASA and private companies like SpaceX talk about sending humans to Mars, the mission architectures often include nuclear thermal propulsion as the enabling technology for the journey. The modern designs for these engines, while improved with new materials and computer modeling, are direct descendants of the pioneering work done on those clandestine Soviet missions. The data on radiation effects and material science gathered from the Topaz flights is still used today to validate computer models and inform safety protocols. This hidden chapter of the space age, conducted in utter secrecy for national strategic reasons, ultimately laid the essential groundwork for what may become humanity's most ambitious peaceful journey, proving that even the darkest corners of the Cold War can eventually light the way to the stars. But the quest for the perfect unseen eye did not stop with the technological leaps of earlier programs. As the Cold War drew to a close and the world entered the more complex and unpredictable landscape of the 1990s, the nature of global threats began to shift, demanding a new kind of watchfulness from above. The answer to this new era of observation was not just about seeing more clearly, but about becoming utterly invisible to the very adversaries being watched. This philosophy gave birth to one of the most secretive and technologically ambitious space projects of its time, the Misty satellite program. Initiated by the National Reconnaissance Office and the Central Intelligence Agency, Misty was not merely an upgrade to existing spy satellites. It was a fundamental reinvention of stealth in space. an attempt to create a reconnaissance platform that could operate with near-total impunity over hostile territory, its presence completely unknown to those on the ground. The engineering challenges were staggering, a high-stakes game of cosmic hide and seek. To achieve true stealth in the vacuum of space, the Misty satellites had to solve a multi-layered problem of detection. The first and most obvious challenge was avoiding visual and radar tracking from Earth. This was tackled through a combination of revolutionary materials science and ingenious orbital mechanics. The satellites were likely coated in advanced radar-absorbent materials and perhaps even equipped with light-absorbing, non-reflective surfaces to drastically reduce their visual and radar cross-section, making them appear as tiny, insignificant pieces of space debris to any observer. But perhaps even more cleverly, they were probably placed into unusually high or eccentric orbits, far from the standard paths where other nations would typically focus their surveillance efforts, allowing them to drift unnoticed against the backdrop of stars. Yet the most difficult problem to solve was managing heat. In the freezing cold of space, any object generates a distinct infrared signature from its internal electronics and power systems. To a sophisticated infrared sensor on the ground, a satellite's heat plume is like a bright flare in the night sky, making it easily detectable no matter how visually dark it is. The Misty program almost certainly pioneered revolutionary thermal management systems to overcome this. Engineers would have had to design ways to dissipate the satellite's waste heat in a direction not visible to prying sensors on Earth, or perhaps even develop technologies to mask or redistribute that heat signature entirely, effectively allowing the spacecraft to hide its thermal exhaust. This level of stealth required a complete rethinking of power systems, component layout, and thermal radiators, pushing the boundaries of aerospace engineering into realms previously confined to science fiction. The ultimate goal of this incredible technological effort was persistent, undetectable surveillance. A Misty satellite, once successfully hidden, could loiter over a region of interest for extended periods without the target country ever knowing it was there. This provided a priceless strategic advantage. It could monitor the construction of secret nuclear facilities, track the movements of mobile missile launchers, or watch terrorist training camps, all while its operators enjoyed the complete certainty that their watchful eye was not being watched in return. This changed the very paradigm of intelligence gathering, moving from brief, predictable flyovers to constant, invisible presence. The intelligence gathered in this way was considered so sensitive and valuable that the entire program was buried under an immense classification wall, with its very existence denied for years. While the operational details of Misty remain shrouded in secrecy, its technological legacy has subtly trickled down into the civilian world. The advanced materials developed to make a satellite invisible to radar have found applications in commercial aviation and spacecraft, leading to stronger, lighter, and more durable composites. More profoundly, the sophisticated image analysis software required to interpret data from a platform that might be maneuvering or observing from an unusual angle has directly influenced the algorithms used by modern civilian Earth observation companies. The ability to stitch together clear pictures from less than ideal conditions, a necessity for a stealthy satellite that cannot always optimize its position for the perfect shot, has accelerated the capabilities of services that monitor agriculture, track shipping, and respond to natural disasters. The Misty program, a ghost in the machine of 90s espionage, quietly demonstrated that the ultimate form of power in space is not just the ability to see, but the power to watch without being seen, a lesson that continues to shape both global security and our view of our own planet from the heavens above. While the world watched pioneers 10 and 11 make history as the first human-made objects to travel through the asteroid belt and visit Jupiter and Saturn, a third, identical spacecraft sat quietly in a clean room, its own voyage to the stars forever cancelled. This was Pioneer H, the unused backup, a perfect twin built not for glory but for insurance. In the high-stakes world of early planetary exploration, where a single wiring fault or a tiny meteoroid impact could end a mission millions of miles from home, having a complete, flight-ready duplicate was a necessary precaution. If something catastrophic had happened to either Pioneer 10 or 11 during assembly, testing, or even on the launch pad, Pioneer H was designed to immediately take its place, ensuring that the monumental investment of time and money would not be lost to simple bad luck. It was the understudy patiently waiting in the wings for a call that fortunately never came. With both primary missions achieving spectacular success, NASA faced a decision. The agency briefly considered finding a new purpose for this fully functional spacecraft. Some engineers proposed a unique trajectory that would have sent Pioneer H soaring over the Sun's north and south poles, a journey that would have provided our first three-dimensional view of the heliosphere and solar wind. Others suggested a mission to study the elusive planet Pluto, which at that time was little more than a faint speck of light in even the most powerful telescopes. But ultimately, the funding and launch vehicle were allocated to newer, more ambitious projects like Voyager. Rather than gather dust in a warehouse or be dismantled for parts, Pioneer H was given a different, quieter fate. In a generous and forward-thinking act, NASA donated the complete, pristine spacecraft to the Smithsonian National Air and Space Museum, where it was suspended from the ceiling, a silent monument to what might have been. To the casual museum visitor, it is simply a display, a shiny artifact from a bygone era of space exploration. But for the engineers who designed the Pioneer program, this unflown spacecraft was far from a mere trophy. It was a critical data point and a validation tool of immense value. During the intense preparations for the launches of Pioneers 10 and 11, the backup spacecraft served an essential role on the ground. It was a perfect testbed, an engineering duplicate that could be used to troubleshoot problems without risking damage to the actual flight hardware. If a component on Pioneer 10 was behaving strangely, engineers could replicate the issue on Pioneer H in the lab, running diagnostics and testing solutions in a risk-free environment. This allowed them to solve problems with confidence, ensuring the missions that did fly were as robust and reliable as possible. Furthermore, the very existence of Pioneer H proved the soundness of the original design. The fact that a third spacecraft could be built to the exact same specifications and pass the same rigorous pre-flight tests was a powerful testament to the robustness and repeatability of the engineering. It demonstrated that the Pioneers were not fragile, one-off marvels, but represented a mature, dependable platform that could be reliably reproduced, a crucial step for the future of deep space exploration. The knowledge gained from building and testing this identical twin directly informed the design of the even more ambitious Voyager probes that followed. Lessons in radiation hardening, gained from ensuring the Pioneers could survive Jupiter's brutal magnetic field, were baked into Voyager's systems. The precision navigation techniques perfected for threading the needle through the asteroid belt became standard procedure. Pioneer H's legacy is a profound reminder that in the journey of discovery, not all progress is measured in miles traveled or pictures beamed back. Sometimes the most important missions never leave the ground. This quiet pioneer, suspended in the hushed air of a museum, represents the power of preparation, the value of a well-conceived backup plan, and the undeniable truth that every piece of hardware, whether it flies or not, contributes to the collective knowledge that pushes humanity further into the cosmos. Its story is a tribute to the unsung heroes of engineering, the prototypes, the test articles, and the backups that form the essential, if invisible, foundation for every spectacular success we celebrate. This unassuming spacecraft helped prove that we could build machines tough enough to not only survive the perils of deep space but to thrive there for decades, a lesson that continues to guide every mission we send into the great unknown. While NASA and the Soviet Union were focused on the grand, visible goals of landing on the moon, a far more personal and covert question was being asked in the background. What happens to life itself when it leaves the cradle of Earth? The answer was pursued through a series of public missions that seemed purely noble and scientific, the biosatellite programs. To the world, these projects represented humanity's compassionate curiosity, sending everything from plants and insects to primates and microorganisms into orbit to study the fundamental effects of weightlessness and radiation on biology. The image of a monkey named Gordo or a capsule full of seeds orbiting the Earth was a powerful public relations tool, showcasing space exploration as a peaceful, life-affirming endeavor. But woven into the fabric of these very public experiments was a tightly held, classified thread of military necessity. The brilliant cover story of pure biological research was almost perfect. It was believable, laudable, and it provided a plausible explanation for the odd orbits, specific mission durations, and unique instrumentation. However, hidden within the same capsules that carried fruit flies and bread mold were other, far more sensitive experiments. For the military planners of the Cold War, understanding the effects of the space environment wasn't just about keeping astronauts healthy for a trip to the moon. It was about preparing soldiers for potential future battlefields in orbit. The space radiation that could mutate a simple bacterium could also scramble the delicate electronics of a spy satellite, or, more grimly, cause catastrophic cellular damage to a human crew on a long-duration military mission. The data from these biological passengers provided the first concrete models of how radiation dosage accumulated in living tissue over time in different orbital regimes, information that was absolutely critical for designing protective shielding for both manned military spacecraft and the increasingly sophisticated electronic brains of reconnaissance satellites. This clandestine research went even deeper, focusing on the physiological and psychological toll of spaceflight. While public reports discussed the weightlessness-induced bone loss in a monkey, classified reports were analyzing that same data to determine how long a soldier could remain combat effective in zero gravity before his skeleton began to weaken. Experiments on circadian rhythms in orbit weren't just about astronaut sleep schedules. They were about understanding how to maintain alertness and decision-making capabilities for crews tasked with complex military operations while cut off from the day-night cycle of Earth. The biosatellite missions, in their dual role, became a crucial bridge between the known world of aviation medicine and the entirely new field of space military medicine. They provided the foundational data needed to answer terrifying strategic questions. Could a human actually aim a weapon in microgravity? How would prolonged confinement in a small capsule affect the mental state of a crew on a months-long surveillance mission? The legacy of this blending of goals is deeply embedded in our modern capabilities. The radiation-hardening techniques developed to protect the electronic components tested on these biosatellites became standard for every military and commercial satellite that followed, drastically increasing their lifespan and reliability in the harsh environment of space. The medical data on fluid shifts, muscle atrophy, and immune system response gathered from these early missions directly informed the exercise and countermeasure regimens used by astronauts on the International Space Station today, allowing them to stay in orbit for a year or more without catastrophic health degradation. This secret partnership between biology and technology, between open science and classified defense, accelerated progress at a remarkable rate. It proved that a single mission could serve two masters, answering profound questions about life itself while simultaneously preparing for the sobering reality of war in the final frontier. A quiet convergence of interests that ultimately made all of spaceflight, both civilian and military, far safer and more capable. In 2011, an unremarkable rocket lifted off from California's Vandenberg Air Force Base, carrying a payload known only by its dry, bureaucratic designation, NROL-33. To the handful of observers tracking the launch, this was just another routine mission for the National Reconnaissance Office, the ultra-secretive agency responsible for America's spy satellites. The rocket, a Taurus XL, climbed into the sky as scheduled, its progress normal for the first few moments. Then, without warning, something went terribly wrong. The payload fairing the protective nose cone shielding the precious satellite failed to separate properly. Weighed down by this unexpected burden, the rocket quickly lost momentum, veered off course, and began to break apart. Within minutes, the multi-million-dollar mission, along with its highly classified cargo, was scattered in pieces across the southern Pacific Ocean. To the public and the press, it was a clear-cut, very expensive failure. Headlines briefly noted the loss of a secret government satellite before the world's attention moved on to the next news cycle. The story of NROL-33 appeared to be over almost as soon as it began. But in the world of classified space operations, a public failure is rarely the end of the story. While the satellite itself was lost, the mission was far from a total loss for the intelligence community. The NRO, by its very nature, is a learning organization that treats every launch, whether successful or not, as a data-gathering opportunity. The investigation into the Taurus rocket's failure was swift and brutally thorough, involving a team of top engineers from the NRO, NASA, and the rocket's manufacturer. They pored over every shred of telemetry, every sensor reading from the rocket's brief flight. The culprit was identified as a simple, yet catastrophic, design flaw. A system meant to pyrotechnically split the fairing had malfunctioned due to a faulty actuator. This single point of failure doomed the entire mission. The lessons learned from this forensic analysis were immediately translated into new, stringent engineering requirements for all future launch vehicles contracted by the U.S. government. The failure of L-33 directly led to improved redundancy in separation systems, more rigorous pre-flight testing protocols, and a renewed focus on the often overlooked mechanical components that are just as critical as the advanced electronics they protect. In this way, the very public loss made every subsequent classified launch significantly more likely to succeed, a trade-off that the NRO's planners were willing to accept. Yet, the most intriguing secrets of this mission lie not in the rocket that failed, but in the satellite that never reached orbit. While its exact capabilities remain classified, the L in its designation points to it being part of a series of large, sophisticated signals intelligence satellites, likely destined for a high geostationary orbit. Analysts and amateur satellite trackers who study these things believe it was probably a next-generation eavesdropping platform, designed to be a silent, powerful ear in the sky. Its sensors were almost certainly tuned to intercept a vast range of electronic communications, from diplomatic cables and military radar transmissions to the telemetry from missile tests in denied territories like North Korea and Iran. This was not just a simple replacement for an old satellite. It likely incorporated bleeding-edge technology, perhaps using advanced digital signal processors to sift through the electromagnetic noise of the modern world with unprecedented clarity and speed. The loss of such a capable platform was a serious blow, but the technological breakthroughs achieved in its development were not lost with it. The research and development cycle for such a project generates a wealth of knowledge. The new antenna designs, the more sensitive receivers, the improved encryption algorithms for its data downlink, all of this intellectual property was preserved. It would have been immediately fed back into the design labs, informing and accelerating the development of its successors, making the next satellite in the line even more capable. This hidden cycle of iterative improvement, fueled even by failure, ensures that America's eyes and ears in space are constantly evolving, always staying one step ahead of adversarial countermeasures. Furthermore, a mission like L-33 almost certainly served as a testbed for new stealth and deception technologies, in an era where other nations, notably Russia and China, are rapidly advancing their own capabilities to track and target satellites. Simply parking a large, sensitive listening post in geostationary orbit is no longer enough. The satellite may have incorporated experimental radar-absorbent materials to make it harder to detect from the ground, or innovative maneuvers to mask its true orbit and purpose. It might have tested new ways to hide its thermal signature, making it blend into the cold background of space to avoid infrared detection. The failure of the launch denied operators the chance to test these systems in the real environment of space, but the concepts and ground testing behind them were undoubtedly validated and refined. The mission's legacy, therefore, is a paradox, a very public symbol of fallibility that nonetheless quietly reinforced the relentless, unseen march of technological progress in the shadows, proving that even in the 21st century, a lost courier can still deliver its most important message. While the world held its breath watching Apollo 11's lunar module descend toward the Sea of Tranquility, a second, secretive spacecraft was also racing toward the Moon, its trajectory far from the celebratory global broadcast. This was the Soviet Union's Lunar 15, a last-ditch, desperate attempt to upstage the American triumph by achieving an even more spectacular technological feat, an automated lunar sample return. The mission was the culmination of years of covert development, a complex robotic system designed to land on the Moon, scoop up a handful of soil, and then blast back off to deliver its precious cargo to Earth, all without any human intervention. It was a bold, audacious plan, a high-stakes gamble meant to snatch a propaganda victory from the jaws of defeat by proving that Soviet robotics could match or even surpass the efforts of American astronauts. The tension in the Soviet control rooms was palpable, a stark contrast to the public optimism emanating from Houston. Engineers knew they were attempting something incredibly difficult under immense pressure. Lunar 15 was not a simple lander, it was a two-stage vehicle. The bottom half was a landing platform equipped with engines and fuel to perform a controlled descent. Perched on top was a small ascent stage, a compact rocket containing a sealed capsule for the lunar soil and its own engine to launch it back into space for the journey home. The entire sequence had to be flawlessly automated, a delicate ballet of braking, landing, sampling, and launching, all commanded by timers and a rudimentary computer millions of miles from help. As Neil Armstrong and Buzz Aldrin walked on the surface, Lunar 15 was already in lunar orbit, a silent, robotic competitor circling overhead, its controllers frantically analyzing the terrain below to choose a safe landing site far from the Americans. The chosen landing zone was in the rugged highlands near the Sea of Crises, a geologically interesting area that promised different soil samples than those being collected by the astronauts. But the terrain was treacherous, far more so than the relatively smooth mare where Apollo had touched down. On July 21, 1969, just as the Apollo 11 astronauts were preparing to lift off from the Moon, Lunar 15 fired its descent engines and began its final approach. For a few minutes, it seemed the gamble might pay off. Telemetry confirmed the braking burn and the orientation for landing. Then, abruptly and catastrophically, the signal vanished. Later analysis would suggest that the lander, likely confused by the unexpected radar echoes from the rough highland terrain, either crashed into a mountainside or descended too rapidly, smashing itself to pieces on the lunar surface. In an instant, the dream of a robotic sample return victory was vaporized, another Soviet spacecraft lost on the harsh, gray landscape. To the outside world and to history books for decades, Luna 15 was simply a footnote, a pathetic also-ran that failed spectacularly on the same day humanity triumphed. It was easy to dismiss it as a desperate, clumsy failure, evidence of a space program falling hopelessly behind. But this public perception masked the mission's true, hidden value. For the Soviet engineers, the telemetry stream from those final moments was a treasure trove of hard-won data. They now knew exactly how their landing radar had behaved in an unfamiliar environment. They had precise information on the performance of the descent engines under real lunar conditions. They understood how the spacecraft structure had handled the stresses of the landing burn. Most importantly, they knew what hadn't worked. This was not a total loss. It was the most expensive and valuable field test imaginable. Every byte of data from that crash was meticulously analyzed and fed directly back into the design bureau. The algorithms for the landing radar were completely rewritten to better handle rough terrain. The guidance software was refined to be more adaptive. The design of the sampling mechanism was toughened up. Just 9 months later, in September 1970, the Soviet Union tried again with Luna 16. This time, the mission was a flawless textbook success. The spacecraft landed softly in the Sea of Fertility. Its drill bored into the soil, collected over 100 grams of material, and the ascent stage flawlessly launched it back to Earth, where the capsule parachuted down onto the steppes of Kazakhstan. It was a stunning technological achievement, the first robotic sample returned from another celestial body, and it succeeded almost entirely because of the brutal, unpublicized lessons learned from its sacrificed predecessor. The ghost of Luna 15 was in every gram of soil that Luna 16 brought home. This quiet legacy of learning from failure extends far beyond the Soviet program. The knowledge gained from these early automated sampling attempts, including the hard lessons from crashes, profoundly influenced the entire field of robotic exploration. The techniques for core drilling and soil encapsulation pioneered for Luna informed the design of sampling systems on later missions to Mars and asteroids. The iterative process of test, fail, analyze, and improve, demonstrated so starkly by Luna 15 and 16, became a core tenet of engineering for all spacefaring nations. It proved that a very public failure could be the essential foundation for a future, quiet success, a reminder that in the relentless pursuit of progress, sometimes the most important missions are the ones that vanish without a trace, their greatest contribution being the knowledge of what not to do next time. Even as the superpowers were launching robotic spies and secret stations, a different kind of sentinel was being placed into orbit, one with a singular, sobering mission: to ensure that no nation could secretly shatter the fragile peace with a nuclear surprise. The Vela Hotel satellites, a series of 12 spacecraft launched between 1963 and 1970, were the orbiting guardians of the Partial Nuclear Test Ban Treaty, which had outlawed nuclear explosions in the atmosphere, underwater, and in space. Their job was to watch, incessantly and impartially, for the unmistakable double-flash signature of an atomic detonation. The brilliant initial flash of light followed an instant later by a second, broader pulse as the fireball expanded and cooled. This specific fingerprint was something that no natural phenomenon, not even the most violent lightning storm, could replicate. To maintain absolute neutrality and avoid any accusations of espionage, these watchful eyes were placed in incredibly high orbits, over 60,000 miles from Earth, giving each satellite a continuous view of nearly the entire planet's surface and the space around it. They were the ultimate arbiters of trust in an era defined by mistrust, a technological promise that cheating would be seen. For years, the Vela satellites performed their intended duty with quiet, flawless precision. They monitored the world and detected no violations of the treaty, a negative result that was in fact a resounding positive, providing the stable, verified foundation that allowed for further arms control agreements. Their success was a quiet triumph for global security, but then, beginning in 1967, the sensors on these nuclear sentinels began picking up something utterly baffling. Their sensitive X-ray and gamma-ray detectors were being triggered by incredibly powerful, unimaginably energetic bursts of radiation, but these events were all wrong. They weren't coming from the Earth below. They were originating from deep space, from random points across the cosmos, and they were gone in an instant, lasting only a few seconds at most before vanishing without a trace. The initial reaction within the top-secret military and intelligence circles that received these reports was one of deep suspicion. Had the Soviets, or perhaps another unknown power, developed a terrifying new weapon? A bomb that could be detonated in the depths of space? The data was immediately classified at the highest level and subjected to intense, anxious scrutiny. A small team of analysts was tasked with solving the mystery, and they quickly ruled out a terrestrial or human cause. The bursts were distributed evenly across the sky, not clustered around the Earth or along the plane of our solar system. They were coming from everywhere, which meant their source had to be cosmological, originating far beyond our own galaxy. The energy involved was staggering. In a few seconds, a single one of these gamma-ray bursts released more energy than our Sun will emit in its entire 10-billion-year lifetime. The Vela satellites, designed to watch for the end of the world, had instead stumbled upon the most violent and explosive events in the entire universe since the Big Bang itself. This presented a bizarre dilemma for the U.S. government. How do you announce the discovery of a terrifying new astronomical phenomenon without revealing that you made the discovery with a top-secret nuclear surveillance system? The answer was to slowly, carefully, drip-feed the information into the scientific community. Data was declassified in pieces, and the discovery was quietly presented to astrophysicists, who were initially deeply skeptical. How could something so powerful leave no visible trace? For over a decade, the true nature of gamma-ray bursts remained one of the greatest mysteries in science, all thanks to the accidental data collected by a lost mission whose primary purpose was to look the other way. The ultimate legacy of the Vela program is a perfect testament to the law of unintended consequences in space exploration. Its primary mission was an unqualified success in the field of global security, providing the verified trust that helped prevent nuclear proliferation and stabilize a dangerous world. But its accidental, secondary discovery fundamentally rewrote the textbooks of astrophysics. The mystery of gamma-ray bursts consumed the scientific community for decades, eventually leading to dedicated space telescopes that revealed their origins. The catastrophic collapse of massive stars into black holes in distant galaxies, and the mergers of incredibly dense neutron stars. These events are now understood to be the cosmic forges where heavy elements like gold and platinum are created and scattered across the universe. The watchful eyes meant to guard against humanity's capacity for self-destruction instead opened a window into the violent, creative processes that built the very cosmos we inhabit. proving that even a mission focused intently on Earth could not help but make profound discoveries about the universe beyond. While the Vela satellites were silently cataloging the universe's most violent explosions, a much more terrestrial form of violence was being rehearsed in the secretive depths of the Soviet space program. The concept of space as a sanctuary for peaceful exploration was, for military planners on both sides of the Iron Curtain, a naive fantasy. The reality was that the ultimate high ground would also be the ultimate battlefield, and control of orbit could decide the fate of a global conflict. This chilling philosophy drove the development of one of the Cold War's most provocative and clandestine programs, the Soviet Istribitelь Sputnikov, or Satellite Destroyer System, known by its acronym ISA. Beginning in the late 1960s, a series of unassuming Cosmos satellites lifted off from the Baikonur Cosmodrome, their public designations suggesting they were routine scientific or technology demonstration missions. In truth, these were the first dedicated anti-satellite weapons, robotic hunters designed to seek out and physically destroy other spacecraft in a terrifying demonstration of orbital warfare. The method of destruction was as brutal as it was effective. Unlike modern concepts that use lasers or electronic jamming, the ISA system was a co-orbital interceptor. A killer satellite would be launched into an orbit that would eventually bring it close to its target. As it neared, using a sophisticated radar homing system, it would calculate a final intercept course. Then, in a final suicidal act of robotic aggression, it would not fire a missile or laser, but would instead detonate a massive conventional explosive fragmentation warhead, shredding both itself and its target in a cloud of high-velocity shrapnel. This wasn't a precise disabling, it was a total, violent obliteration designed to leave no doubt about the outcome. The tests were conducted under a thick veil of secrecy, often announced as tests of spacecraft rendezvous and docking procedures, or investigations into the conditions of near space, a masterclass in plausible denial that masked their truly hostile intent. The technological challenges were immense. Success required an incredible mastery of orbital mechanics, precise radar tracking, and autonomous guidance, as radio commands from Earth would take too long for the final, split-second intercept maneuver. Each test, whether a success or a failure, generated a treasure trove of data on how to track a small, fast-moving object in the complex environment of space, how to predict its path, and how to maneuver another object into its destructive path. This knowledge is the very foundation of what we now call space situational awareness, the critical ability to know where every object is in orbit and where it is going. While the Soviets were developing this expertise for attack, they were simultaneously and unintentionally pioneering the fundamentals of defense. The same tracking data that allowed a killer satellite to find its prey is used today to warn the International Space Station to dodge a piece of dangerous debris. The orbital models refined for interception are now vital for protecting multi-billion-dollar assets from accidental collisions. For over a decade, the Soviet Union conducted these covert tests, creating a hidden arsenal in the sky and proving that no satellite was safe. The program forced the United States to respond in kind, sparking a secret arms race in orbit that diverted billions of dollars and immense intellectual effort away from peaceful exploration and toward the specter of space combat. The doctrine of mutually assured destruction, which had stabilized the nuclear standoff on Earth, now had a terrifying new dimension in space. The silent, unacknowledged warriors of the ISA program never fired a shot in anger, but their very existence fundamentally altered military strategy, cementing the concept that dominance in space was not just an advantage, but a necessity for national survival. Their legacy is a double-edged sword. The same technology that could start a war in heaven now helps to keep the peace, a permanent reminder that the line between discovery and destruction in the final frontier is perilously thin. But as the silent warriors of the ISA program demonstrated the potential for violence in orbit, a new, more subtle form of power was being perfected, one that traded the brute force of explosions for the immense strategic value of economic insight. While the world became familiar with the stunning photographic images from spy satellites, a different kind of eye was opening in the sky, one that could see through clouds under the cover of darkness and even penetrate the shallow surface of the Earth itself. This was the capability offered by radar imaging, and its most sophisticated expression was the Lacrosse satellite series, a fleet of American spacecraft whose true mission was to become the ultimate economic spies. Launched from the late 1980s onward under the vague and unassuming cover of Earth resources monitoring, these satellites represented a quantum leap in surveillance, moving beyond counting tanks and missiles to tracking the very pulse of a nation's economic engine. The genius of Lacrosse lay in its synthetic aperture radar, or SAR. Unlike a camera that needs sunlight to see, radar works by actively transmitting microwave signals toward the Earth and then meticulously analyzing the returning echoes. This allows it to create incredibly detailed images regardless of weather conditions or the time of day. A thick blanket of clouds over the Amazon rainforest, a pitch-black night over the Siberian tundra, or a dense sandstorm in the Arabian desert, none of these were obstacles for Lacrosse. Its powerful radar beams pierced right through, rendering the concept of hiding from satellite observation almost obsolete. Officially, this capability was promoted for benign scientific purposes, monitoring deforestation, tracking sea ice for shipping, and studying geological formations. And while it certainly did all of these things, its primary gaze was fixed on targets of immense economic and strategic significance. From its polar orbit, Lacrosse could monitor the output of oil fields by measuring the precise levels of crude in storage tanks. It could count the number of cars in factory parking lots in real time, providing an astonishingly accurate proxy for industrial production rates. It could watch the construction of new dams in China, the expansion of port facilities in Iran, or the logging operations in the Congo Basin. This wasn't just about gathering intelligence for a potential conflict. It was about gaining a persistent, undeniable understanding of a rival's economic health and intentions. The data flowing from Lacrosse gave American policymakers and economic analysts a god's eye view of global commerce. If wheat production was collapsing in Russia, the US could anticipate a need to sell its own grain reserves and adjust markets accordingly. If China was suddenly stockpiling rare earth minerals, it could signal an upcoming shift in manufacturing or a potential play for market dominance. This information was power, the power to anticipate market shocks, to negotiate from a position of absolute knowledge, and to shape global economic policy with a clarity no other nation possessed. The existence of the Lacrosse program was an open secret among defense analysts, but its breathtaking capabilities and the specific economic intelligence it gathered remained among the most closely guarded secrets of the Cold War and its aftermath. Its legacy, however, is visible everywhere in our modern world. The advanced SAR technology perfected in secret for Lacrosse is the direct ancestor of the radar systems used by countless civilian Earth observation satellites today. The very same ability to see through clouds and darkness now helps scientists track the minute movements of glaciers, assists emergency responders in mapping flood zones after a hurricane, and enables archaeologists to discover lost cities hidden beneath dense jungle canopies. A tool developed to count an adversary's economic assets quietly evolved into an instrument for understanding and protecting our planet. proving once again that the most impactful missions are often those that operate in plain sight, their deepest secrets and greatest contributions remaining hidden in the echoes of their own radar beams. While the world marveled at the first images beamed back from the surface of the Moon by the Soviet Union's Lunakhod 1 rover in 1970, a perfect twin of that pioneering machine sat in a sterile warehouse, its own wheels forever clean of alien dust. This was the Lunakhod backup vehicle, an insurance policy built for a mission so audacious that failure seemed more likely than success. Sending a remotely controlled vehicle to drive across another world was an unprecedented challenge, a feat that required solving problems in mobility, power management, thermal control, and communications that had never been attempted before. The backup rover was not a mere display model. It was a fully functional, flight-ready duplicate, a silent servant standing by in case its sibling was lost to a rocket explosion, a crash landing, or the unforgiving harshness of the lunar environment. Its very existence was a testament to the immense value and risk associated with this groundbreaking endeavor. When Lunakhod 1 defied the odds and became a spectacular success, trundling across the sea of rains for 11 months and sending back thousands of pictures, the backup's primary reason for being vanished. It was never called upon to make the journey to the Moon. In a more simplistic narrative that would be the end of its story, a relic of a road not taken, a technological artifact left to gather dust in a museum. But for the engineers and scientists who understood the iterative process of exploration, this dormant machine was not a dead end. It was a living laboratory, a priceless testbed whose value was only just beginning. Freed from the intense pressure of an imminent launch, the backup rover became a platform for relentless experimentation and refinement, a sandbox where engineers could play with ideas too risky to try on the active mission millions of miles away. They subjected the duplicate to brutal stress tests, pushing its 8 independently powered wheels over simulated lunar terrain, far more rugged than anything the real Lunakhod would ever encounter. They ran its systems for weeks on end, far exceeding its designed operational lifetime, to identify potential points of wear and failure that could be redesigned for greater resilience. Most importantly, they used it to develop and torture-test new software algorithms for autonomous navigation. The original Lunakhod was notoriously difficult to drive, with its human operators on Earth dealing with a several-second communication delay that made every command a careful, deliberative process. The backup vehicle allowed them to experiment with proto-autonomy, teaching the rover to recognize obstacles on its own and make simple decisions to avoid them, thereby reducing the cognitive load on its drivers and preventing it from getting stuck in a crater or tipping over on a slope. This quiet, Earth-bound research program, conducted on the unused backup, generated a wealth of practical knowledge that became the invisible inheritance for every planetary rover that followed. 2 decades later, when NASA's Jet Propulsion Laboratory was designing the tiny Sojourner rover for Mars, they faced the same fundamental challenges the Soviet engineers had wrestled with: how to build a robust mobile platform that could survive extreme temperature swings, navigate unknown and treacherous terrain, and operate with a degree of independence from its human controllers. The lessons learned from testing the Lunakhod backup directly informed the design principles for Sojourner's rocker bogie suspension system, a masterpiece of engineering that keeps all 6 wheels on the ground even when climbing over large obstacles. The early autonomous navigation algorithms refined on the test rover paved the way for the increasingly sophisticated self-driving software that would later allow rovers like Spirit, Opportunity, and Curiosity to plan their own routes across the Red Planet. The silent servant never left Earth, but its legacy is etched into the tracks of every robot that has since roved across another world, a powerful reminder that in the grand story of exploration, progress is built as much in the quiet workshops on our own planet as it is in the dramatic triumphs on distant frontiers. While massive observatories like the Solar Dynamics Observatory captured the public's imagination with their stunning high-definition images of the Sun, a far smaller and quieter mission was also making its way to orbit, armed with a deceptively simple goal. The Picard spacecraft, named not for the famous Star Trek captain but for the 17th-century French astronomer who first measured the Sun's activity, launched in 2010 with a modest but critically important task: to measure the total and spectral solar irradiance with exquisite precision. In an era of billion-dollar flagship missions, this French-led project with international partners was a shoestring operation, a dedicated specialist focused on a single question that held the key to understanding Earth's climate system. How much exactly does the Sun's energy output vary, and how do those subtle fluctuations directly influence our planet's atmosphere and climate patterns? While other missions studied solar flares and coronal mass ejections, Picard was tasked with listening to the Sun's heartbeat, monitoring its fundamental pulse with a stability and accuracy never before achieved. Its most significant contribution was in refining our models of what scientists call space weather, the complex interactions between solar activity and Earth's magnetic field and atmosphere. Picard's incredibly precise data showed that the Sun's energy output was even more variable than previously thought, with subtle dips and peaks that corresponded closely to the formation and dissipation of sunspots. This wasn't just an academic observation, it was a crucial piece of the climate puzzle. These minute changes in solar irradiance have a direct, though small, impact on the temperature and chemistry of Earth's upper atmosphere. By quantifying this relationship with unprecedented accuracy, Picard provided the essential data needed to separate the Sun's influence from the much larger signal of human-induced climate change. This allowed climate scientists to create far more accurate and defensible models, removing a significant source of uncertainty and providing a clearer picture of our planet's warming trajectory. In the heated debates over climate science, the quiet, objective data from this forgotten mission became an unassailable bedrock of fact. Yet, perhaps its most fascinating discovery lay in its measurements of the Sun's diameter. Picard confirmed with great certainty that the Sun is not a static sphere of fire. It actually pulsates very slightly, breathing in and out over cycles tied to its magnetic activity. These tiny changes in diameter, on the scale of mere kilometers across a sphere over 1 million kilometers wide, are nonetheless significant. They are the physical manifestation of the turmoil happening deep within the Sun's convective zone, and they provide a unique window into the internal processes that drive the solar dynamo. Understanding this mechanism is the holy grail of heliophysics, as it would allow us to finally predict the Sun's long-term behavior with confidence, forecasting the strength of future solar cycles and their potential impacts on our technology-dependent civilization. Picard data on these oscillations became a treasure trove for solar physicists, offering clues to mysteries that larger, more generalized missions simply weren't equipped to solve. Despite these profound contributions, the Picard mission remains almost entirely unknown outside a small circle of specialists. It operated in the long shadow of its larger, more glamorous cousins, quietly collecting its data for 6 years without fanfare or dramatic public announcements. Its end was as understated as its beginning. After a successful mission, it simply re-entered Earth's atmosphere in 2018, burning up unnoticed. But its legacy is permanently encoded in the sophisticated climate models we use today to predict future warming scenarios and in our improved understanding of the Sun's inner workings. Picard proved that a mission doesn't need a giant budget or a high-profile launch to make a monumental difference. Sometimes, the most critical discoveries come from a dedicated specialist focused on a single, fundamental question, a hidden heliophysicist silently watching the sun so we can better understand our own world. This sets the stage for an even more ambitious and secretive endeavor, one that moved beyond observing our own star to testing the very technologies that might one day carry us to others. But long before the Breakthrough Starshot initiative captured headlines with its visionary goal of sending gram-scale probes to another star within a generation, the fundamental technologies needed for such a journey were being tested in absolute secrecy, hidden within the classified portfolios of the world's most advanced aerospace agencies. These weren't grand, publicly celebrated missions with names and launch dates, but rather a series of black-budget research projects, experimental payloads, and technology demonstrators that quietly pushed the very boundaries of physics and engineering. The concept of a light sail, for instance, using the gentle but constant pressure of photons from a laser or the sun itself to propel a spacecraft, seems like a fantastical idea from science fiction. Yet, declassified documents and the careful analysis of amateur satellite trackers suggest that experimental tests of solar sail materials and deployment mechanisms were likely conducted under the guise of other, more mundane military or scientific missions throughout the late 20th century. A satellite launched to study communications might have also carried a small, folded package of ultra-thin, reflective mylar, secretly unfurling it in orbit to test its stability and response to solar radiation pressure, gathering data on a propulsion system that requires no fuel whatsoever. The parallel challenge of miniaturization was equally advanced behind this classified curtain. The driving force behind Breakthrough Starshot is the idea of a star chip, a fully functional spacecraft the size of a postage stamp, packed with cameras, sensors, and communications equipment. Shrinking complex systems to such a microscopic scale is a monumental task, one that draws directly from the world of microelectronics and nanotechnology. The development of spy satellites, which demanded ever more powerful cameras and sensors in ever smaller and lighter packages to fit on smaller, cheaper rockets, created a relentless pressure to miniaturize. The same government research arms that funded stealth aircraft and precision-guided munitions were also pouring money into advanced micro-electromechanical systems, quantum dot sensors, and radiation-hardened microprocessors. The tiny gyroscopes that keep your smartphone level and the incredibly sensitive accelerometers that trigger your car's airbags are commercial descendants of this kind of research. It is almost certain that prototypes of the very components needed for an interstellar nanocraft, miniaturized thrusters for attitude control, powerful lasers for communication across light years, and ruggedized power systems were developed and tested in laboratories so secure that their very existence was unknown, their breakthroughs filed away in reports seen by only a handful of clear individuals. These clandestine research efforts, though disconnected and hidden, collectively formed the essential bedrock upon which all modern interstellar ambition is built. They provided the initial, hard-won data points that proved such technologies were not entirely the stuff of dreams. They answered the fundamental, preliminary questions. Could a sail made of material only a few hundred atoms thick survive the rigors of launch and deployment? Could a laser beam be focused tightly enough over vast distances to provide meaningful acceleration? Could a computer the size of a fingernail process complex commands and transmit data across the interstellar void? The answers, painstakingly gathered in secret, moved these concepts from the realm of pure theory into the domain of engineering feasibility. This hidden groundwork de-risked the most audacious aspects of projects like Starshot, giving its founders the confidence to invest serious scientific and financial capital into the endeavor. The quiet quest conducted in the shadows of national defense and intelligence created a silent, invisible bridge between the science fiction of yesterday and the scientific reality of tomorrow, proving that the greatest journeys often begin not with a triumphant launch, but with a series of forgotten experiments whose true purpose was understood by only a very few. When we stitch together the stories of these 21 lost missions, a fascinating tapestry emerges, revealing patterns that tell us far more about the journey into space than any single success story ever could. One of the most persistent threads is the deliberate and ingenious blending of scientific pursuit with national security. This was never a simple case of one masquerading as the other. It was a sophisticated fusion where each discipline profoundly advanced the other. The OAO-2 Astronomical Observatory that also monitored for nuclear tests, or the biosatellite missions that studied biological effects while secretly gathering data to harden electronics against radiation. These were not cynical deceptions but masterclasses in efficiency. They proved that the same exquisite sensitivity required to detect a faint star's ultraviolet light could be tuned to identify the unique flash of a missile launch. This convergence created a powerful feedback loop. The relentless demands of espionage drove the development of ever more sensitive and reliable sensors, which in turn supercharged the capabilities of pure scientific instruments. The technologies refined in the shadows for listening to enemy radar or seeing through cloud cover became the very same tools that now allow us to peer to the edge of the observable universe and monitor the health of our own planet's ecosystems in real time. This duality, born from Cold War necessity, ultimately accelerated progress for all of humanity, demonstrating that the path to discovery is rarely straight and often walks a line between different kinds of ambition. Equally important is the hidden role of failure in this narrative. For every triumphant moon landing or successful planetary orbit, there were dozens of missions that vanished into the ocean, crashed into alien landscapes, or simply fell silent in the void. The Soviet Lunar E-6 No. 2 probe that smashed into the moon, or America's Mariner 8 that never made it out of Earth's atmosphere, were publicly recorded as losses and quickly forgotten. But behind the scenes, these were not endings. They were the most expensive and valuable field tests imaginable. Each failure generated a torrent of crucial data on what not to do. A malfunctioning valve, a misaligned gyroscope, or a flawed software algorithm, each mistake was a lesson etched in metal and fire, forcing engineers to go back to their drawing boards and create more robust, more resilient, and more intelligent systems. The spectacular success of the Mars rover's spirit and opportunity, for instance, stands directly on the shoulders of the very public failure of Mars Observer. Its loss catalyzed a complete philosophical shift at NASA toward the faster, better, cheaper model that made those rovers possible. This process reveals a fundamental truth of innovation. Progress is not a linear path of victories, but a messy, iterative climb where the forgotten setbacks provide the essential footholds that make the next ascent possible. And then there is the overarching legacy of secrecy itself, a double-edged sword that both propelled and hindered our reach for the stars. On one hand, the veil of classification allowed for rapid, focused, and well-funded progress. Unburdened by public scrutiny or international oversight, engineers could pursue audacious ideas like nuclear thermal rockets or stealth satellites, making leaps in technology that might have been deemed too risky or controversial in an open forum. This environment of intense competition and absolute secrecy drove an astonishing pace of innovation in areas like materials science, miniaturization, and propulsion. However, this same secrecy came at a significant cost. It stifled collaboration, forcing brilliant minds on both sides of the Iron Curtain to waste precious time and resources solving the exact same problems in parallel. It created a dangerous fog around military activities in space, raising the terrifying prospect of miscalculation and escalation. Perhaps most tragically, it delayed the broader scientific and cultural benefits of these discoveries. The Vela satellite's accidental discovery of gamma-ray bursts, for example, remained a classified mystery for years, slowing astrophysics until the data could be carefully released. Secrecy compartmentalized knowledge, protecting national interests in the short term, but potentially slowing the collective advancement of our species in the long term. Yet, the ultimate testament to these lost missions is not found in classified reports or museum displays, but in the fabric of our daily lives. Every time you use your smartphone to navigate with GPS, you are leveraging a technology that was refined and protected by secret military satellites. The accurate weather forecasts that plan your weekend are powered by climate models informed by solar data from missions like Picard, and by Earth observation techniques perfected by covert programs. The global communication networks that connect us instantly rely on satellite technology, advanced by the need to transmit stolen data securely across the world. These hidden endeavors changed everything by first changing nothing in the public eye. They operated in the background, solving immense technological challenges whose solutions quietly trickled down into the civilian world, often without anyone knowing their origin. They remind us that history is a story written not only by the triumphs we celebrate, but by the countless quiet efforts, the failed attempts, and the secret experiments that collectively paved the way. As we stand on the cusp of a new era with private companies fueling a space renaissance and nations again looking toward the Moon and Mars, the lessons of these lost missions are more relevant than ever. They teach us the value of ambition, the importance of learning from failure, and the need to balance necessary secrecy with the ultimate goal of open discovery for all humankind. From covert satellites to forgotten failures, these 21 lost space missions have indelibly shaped our world, advancing technology, science, and security without fanfare. They teach us that progress often occurs in the shadows, driven by curiosity, necessity, and sometimes secrecy. Think about the last time you used your phone to navigate through an unfamiliar city. That seamless guidance is powered by the Global Positioning System, a technology whose early development was heavily informed by the precise timing and orbital tracking requirements of clandestine signals intelligence satellites like Relevance. Or consider the accurate weather forecasts that help you plan your weekend, which rely on climate models refined by solar irradiance data from missions like Picard, a mission that operated in the shadows of larger, more famous observatories. These hidden endeavors didn't just alter the course of the Cold War, they quietly built the technological bedrock of our modern, interconnected daily lives, proving that the most profound revolutions are often the ones nobody sees coming. This journey through the archives of space history reveals a powerful truth. Our future is often built upon the quiet, unseen foundations of the past. As we stand on the cusp of a new space age, with ambitious plans to return to the Moon and venture onward to Mars, the lessons from these lost missions are more relevant than ever. The iterative process of learning from failure, so starkly demonstrated by the Soviet Lunar program or NASA Mariner 8, is now a core tenet of modern engineering. Private companies embracing the test often, fail fast philosophy are directly channeling the hard-won wisdom from these early, very public setbacks. The daring convergence of science and security, pioneered by missions like 002, continues today as agencies partner with commercial entities, blending exploration with economic opportunity in ways that would have been unimaginable just a few decades ago. The next great breakthrough, the propulsion system that gets us to Mars in months instead of years, the life support system that allows for permanent settlements, or the communication technology that links entire planets, might very well be under development right now in an unmarked facility. Its world-changing potential known only to a small team of engineers bound by secrecy. The story of space exploration is still being written, and its next pivotal chapter is likely being drafted in the same quiet, determined spirit that defined these 21 hidden gems. We hope you've enjoyed this deep dive into the forgotten corners of space history. If these untold stories of ingenuity and perseverance captivated you, please show your support by liking this video and subscribing to our channel for more journeys into the hidden narratives that shaped our world. We'd love to hear which of these lost missions surprised you the most. Was it the silent listeners of the Rhyolite program, the robotic lunar samplers of the Soviet lunar missions, or the stealthy watchfulness of Misty? Share your thoughts and questions in the comments below. We read every single one. Thank you for watching, and remember, whether you're gazing up at the stars or simply glancing at the map on your phone, you're interacting with a legacy built by dreams, determination, and a surprising number of secrets. Keep looking up, there's always more to discover.